Hey folks, we are on the Unit 3 Day 6 lesson and we're looking at the intersection of two lines. In the first part of this lesson we found the intersection of a line and a plane, and now we're going to talk about two lines in 3 dimensions. So we know in R2, just kind of make a note up here I think. So in R2 we have, and this was like grade 10, all of those POI things. You could have two lines that had, most often, right? We were solving and we got one POI. Or you could have two lines and maybe they are parallel, and they would have 0 or no POIs. Or you could have two lines and they're actually right on top of each other, and that's what we call coincident. And we have infinite numbers of points of intersection. So all of the points that are on one line are also on the other. So in R3, we are still going to have these 3 cases. We could have lines that cross and touch in one point. We could have lines that are parallel and don't touch at all. We could have two lines that might look very, very different but are actually the same line. But there's also a 4th case, and we're going to look at that. So the first 2 cases are where they actually have a solution. So the first case is, again, probably what most people are going to think of when talking about intersections. The lines cross and they touch at one point and you can solve for that point. Okay, so this has 1 POI. The second case is if we have those coincident lines. These 2 lines are the exact same line. Because we don't have unique equations, they might look very different, but you have infinite points of intersection. That's kind of bad notation, but hopefully you guys will understand what I mean there. The next case is the same as in R2. If you have parallel lines, you have no points of intersection, but in R3, we have this 4th case that doesn't come up in R2, and that's called skew lines. So these lines do not intersect, but they're also not parallel. Now that's not possible in 2 dimensions. If you have 2 lines that are not going to cross in R2, for sure they have to be parallel. But in R3, and just kind of hold up 2 pencils at your desk right now, you could have 2 lines going like this, and these lines, my blue pen and purple pen, are never going to touch, but they actually are not, very clearly not parallel. So you can get no points of intersection on lines in R3 even if they're not parallel, and that's called skew lines. And this also has no points of intersection. So we'll look at how to tell the difference between these 2 cases if we're trying to solve for those. Okay, so the first example here, we're given 2 equations of lines. The first one is written in parametric form, and the second one is written in the vector form. When we're solving for points of intersection of lines, we're going to, like we wanted with the equations of the planes, we want these to be all in parametric form. Okay, so I'm going to rewrite these. The second one, L2, in parametric. So L1, I have x equals -3 minus t, y equals 1 plus t, z equals 4 plus 4t. And I may write this also just so we can kind of see in our vector form. So the position would be negative 3, 1, 4 plus t times the direction would be negative 1, 1, 4. And L2, it's given to us in the vector form, but I want to rewrite this as, whoops, forgot my t is a real number. I want to rewrite this in terms of the parametric with x equals y equals z equals. So x is going to be 1, minus 6a, y is 4 plus a, and z is 6 plus 6a. So there's one thing we always want to check, and that is whether it's one of the cases where you have direction vectors that are scalar multiples. So in this one, if with the parallel lines, you would have direction vectors are scalar multiples, and this can save you a little bit of work. And this one, of course, where they're the same line, you would have direction vectors are scalar multiples. So if you get a situation where the direction vectors are scalar multiples, then you really just have to kind of choose, and I'll slide both of these on, whether you've got case 2 where it's the exact same line or case 3 where they're parallel. And you can do that by just checking a point on one line and see if that point is on the other line. So that's a much easier calculation than what we're going to do here. And I wouldn't recommend trying to solve for the point of intersection if you noticed this kind of special property. But when we're taking a look at this one, we see that the direction vector here is negative 1, 1, 4, and the direction vector here is negative 6, 1, 6. So they're definitely not scalar multiples. I'm going to try to solve these. And what we're going to do is create two equations with two unknowns. Because we want to solve basically for the a's and the t's. So I'm going to create two equations with the x and the y, and we'll solve those for a equals something, t equals something. Then we'll check in the z's and we'll determine whether we've got that case 1 where it intersects in one point or case 4 where they don't intersect at all. So I'm going to create an equation with the x's. So I have negative 3 minus t equals 1 minus 6a. So just kind of coming from there and there to put that equation together. And then I'm going to create an equation with the y's. And 1 plus t equals 4 plus a. And you can solve this, like now we're into grade 10 substitution and elimination. You can solve that any way you want. I might, so this is looking pretty easy to rearrange both of these for t actually. I think I'm going to bring this stuff over and the t over to the other side. I'm going to say that this is 6a, and I had negative 3, I'm going to bring a negative 1 over, minus 4 equals t. And then likewise over here, I'll say t equals a, and I have 4 and bring them 1 over, so it's plus 3. So then I have these two equations both equal to t. Depends how it's lined up. If you want to do elimination, you totally can, but I had, two equations where t both didn't have a coefficient. So 6a minus 4 equals a plus 3. So then 5a equals 7, a equals 7 over 5. So solving for that, I get a value for a, and then I'm just going to sub it back in to find t. So t equals 7 over 5 plus 3. T equals, that would be 15 over 5 plus 7 is 22 over 5. Okay. once we get to this point, we really have to check if this is going to be an actual intersection. So this is the point where our x's would be equal and the y's would be equal, but we don't know if the z's would be equal. Is this going to have the same z value in each line? So I'm going to, and like it doesn't look super promising. So I'm going to check the z's. And that looks kind of like a 2, but I'll try and make it look more z-ish. So we know that z equals 4 plus 4t. So 4 plus 4 times 22 over 5. So that would be 20 over 5 plus 88 over 5. So z is 108 over 5. And then we would check the other z using our a value. So z equals 6 plus 6a. So 6 plus 6 times 7 over 5. So that's 30 over 5 plus 42 over 5. 72 over 5. So because these are not equal, if we have the parameters that are needed to get the x's and y's the same, they don't give us the same z value. So we could say, therefore, these lines are skew. No points of intersection. And one last example. So here we have two lines. Again, these are written nice in vector form, which isn't as easy for the solving, but it's actually kind of good for checking to see if you've got parallel lines or potentially coincident lines, and we don't. So we don't have parallel lines here. So this is going to either be the skew lines or the lines where there is an intersection. So I'm going to take each vector equation and rewrite it as parametric. So the first one, I'm going to say x equals 2 plus t, y equals 1 minus t, and z equals negative 2 plus t. And then the second one, I'm going to say x equals 3 plus 2s, y equals 3s, and z equals negative 1 minus s. And just a kind of note of caution, if you yourself are coming up with an equation here, make sure, or if for some reason you're finding that intersection and both of these parameters are written with the same letter, you have to change that. Like if you by chance had just like written two equations of lines and used t for both of them, swap one of them to a different letter because you have to keep those two variables distinct. So from there, I know I can make up three different equations. Well, really like two equations. I typically just use the x and the y's, and then we'll check that in the third pair of equations. So I know that 2 plus t equals 3 plus 2s. And for the y's, 1 minus t equals 3s. And both of these I have a pretty easy to solve for t equation. So I'm going to rearrange this. T equals 2s, and then bringing the 2 over and subtract, I've got plus 1. And here 1 minus 3s equals t. So now I have two equations, both of which are equal to t, and I can pretty easy pop those two equal to each other and solve this for the s value. So 2s plus 1 equals 1 minus 3s. Here I would get 5s equals 0. So s equals 0. And then t equals 2 times 0 plus 1, t equals 1. So here I got parameters of s equals 0 and t equals 1, and that would give me the same x and y value on both of these lines. And then we'll check our z's. So we know in the first equation, z equals negative 2 plus t. So if t is 1, z equals negative 2 plus 1, z equals negative 1. And in the second one, z equals negative 1 minus s, but s was 0, so z equals negative 1. So this means that there is a point of intersection. If these are equal, there is a point of intersection. Now, be careful, because when we say a point of intersection, we need the x and the y and the z, but we don't have that. We've just got the z, which is negative 1. We have to take these and figure out what the x and the y are. So I'm going to find x and y. You could use either one, the s or the t, but I feel like that's pretty easy to use the 0. So I'm going to be a little bit lazy. So x equals 3 plus 2 times 0. And I'm not showing that s just because I'm running out of space. And y equals 3 times 0. Y equals 0. So then I would just write my POI. The POI is x is 3, y is 0, z is negative 1. So it's actually the one point that was part of the first line there. So those are the different ways of finding intersections. You are going to be responsible for finding intersections of lines with other lines and lines with planes. And over the next few lessons, we're going to start looking at the intersections of 2 or more planes intersecting each other. And that's where we're going to kind of continue on with this.